Okay, so it's worth knowing that there's a trick called reduction of order, which has kind of a strange motivation. So let me pitch to you the situation in which you might find yourself. You might find yourself in this world where you have a second order, what is this thing? Second order?
Linear.
Okay. Second order, linear, non-homogeneous,
not necessarily constant coefficient.
yeah, probs not constant coefficient.
Differential equation.
Okay. So when you find yourself in this particular jungle, right? It's possible. Well, wait. Let me ask, where are you aiming? Like, what is the category of thing you should get at the end?
General.
Yeah, you should get a general solution, right? Which will probably look something like what?
Homogeneous solution plus some other stuff.
It's its own thing.
Yeah, it should look like, okay, y is like a homogeneous part 1, maybe with a constant, plus maybe another constant and a homogeneous part 2, plus maybe some like, yeah, like one particular part or maybe like a bunch of particular parts added together, right? Okay, when do I know how to get to this?
When everything's continuous and nice? Or,
Yeah, and even then I think I really only know how to do this when the constant, when the coefficients are constant, right? You guys see that? Okay, crap. What if the coefficients aren't constant? Wait, hang on. Okay, even if the coefficients are constant, what kind of f's can I make work? Only like really specific ones, right? Like I need an exponential or a polynomial or a sine or a cosine, right? If there's like a secant over there, a secant? You're a dork. You're just not going to get it to happen. What if there's a hyperbolic cosine over there? No, in that case you'd be really lucky because hyperbolic cosine is made out of exponential functions. But in the case of having something else, like a natural log over there, you'd be totally hosed. You guys see this? So reduction of order is a cool trick because I don't care about the forms of P0, P1, P2, or F at all. Right? So this trick rests on an assumption that's not anywhere in evidence. But what you need to make this trick work is you need one of these. So if you have this, so if you have this part, one of the homogeneous bits, you do not have to have both of them, just one of the homogeneous bits, you can get the rest. Cool? This is a miracle. But you have to be able to find one of these, which is itself kind of a tall order, right? You guys remember the trick with the Wronskian we did where it was like, well, if you could find one of the solutions, you could make another one. This is the same thing. This is, if you can find one of the homogeneous bits, you can make the rest of the general solution. You guys cool with that? The procedure for this is a little bit wackadoo. The procedure for this is something like step 1, try variation of parameters, because duh. Guess y, I'm going to put a hat on this. So you might guess y hat is mu times the solution you know, right? You guys want to see what that looks like? Or do you want the rest of the procedure? I'll give you a choice. I can outline the rest of the procedure, or I can show you what that's going to look like in general.
Do both.
Sure. What do you want first? That's what I'm asking. I'm going to do
We already
both.
started it.
Procedure first?
Yeah.
Okay, so after you guess this, something miraculous is going to happen, per usual with good tricks, right? And you're going to get an equation that's first order in mu prime.
So does that mean we won't have any straight mu's? What does
Yeah,
that
there
mean?
won't be any regular mu's. There'll just be a mu double prime and a mu prime. And then you'll do this really funky trick where you just let some new variable, I don't know, z maybe, equal mu prime. Right, that'll bring you to a first order differential equation, which you can solve.
Is that why it's called reduction of order?
That is exactly why it's called reduction of order, right? Because this trick took us from a second order differential equation to a first order differential equation. And I know how to solve first order differential equations.
Like the dirty trick.
It is kind of a dirty trick. But you paid for it, because you had to go find this YH1 someplace. Those things aren't just laying on the ground. You've got to try a lot of stuff to find that thing.
Okay.
Are we going to be given those in the problems, or do
Yeah.
we actually? Okay.
Yeah, so in the book, the homework problems will say things like, here's a differential equation of second order. Knowing that this is one of the solutions of the homogeneous equation, find the general. Cool?
Okay, so say we find our roots, right? And we have like y equals c1 e to the 2x plus c2 x to the 2x. We just use either of those then?
If it's constant coefficient, yeah, you'll know both of them, right? So you could use one. This is not a good trick for if you know both of them, because if you know both of them, well, okay, it's an okay trick if you know both of them.
So this would be like we find one r.
Yeah, this would be like if you only found one of the r's,
And that's what
which isn't really going to happen, right?
yeah, that's why I'm confused.
But this works when the coefficients aren't constant. Remember, the coefficients have to be constant for me to move to that auxiliary equation anyway, for those r's to make sense. So if the coefficients aren't constant, I might be just totally shit out of luck.
Oh, because then we would have like a function times r squared. instead
Yeah,
of
and
just like 3r squared.
yeah, God only knows when that thing's zero, right? Because the x's could play in there.
Could you find a homogeneous case, find a differential equation that's non-homogeneous that works for that case, and then kind of use this trick to find the general solution for that differential equation?
Sorry, say that again?
Like if you just, like if you find a homogeneous solution and then use that for it works for a differential equation?
Yeah, you could use this in place of method of undetermined coefficients if the f didn't match the forms you guys know.
Yeah.
Does that make sense? It's going to be a lot of work, but it would be a method that you could substitute. What is solving for z going to entail? This was the thing I said earlier about this method's a little weird. It's like it kind of clones itself in the process. Yeah, right?
So,
This should be right. So you're going to start this thing with an idea about variation of parameters. You're going to get a new equation that's different, and then you're going to do variation of parameters on that. You guys cool with this? This is a super weird trick. It's very cool that it works. Okay?